In 1981, a small team of astronomers led by Robert Kirshner at the University of Michigan set out to chart the large-scale distribution of galaxies, expecting to find the usual cosmic tapestry clusters, filaments, and voids of modest size. Instead, what they uncovered defied every model and every instinct they had about how matter fills the universe. Their measurements hinted at a vast emptiness, a region so devoid of galaxies that it seemed as if the cosmos itself had been scooped clean. At first, they dismissed it as a data error, perhaps a flaw in instrumentation or a quirk of observational bias. Yet the deeper they looked, the more undeniable the pattern became. Something enormous lurked in the constellation of Boötes, an immense spherical region almost completely hollow, stretching across hundreds of millions of light-years. The discovery would later be named the Boötes Void, and it would challenge nearly every assumption astronomers held about the universe's structure. Before this revelation, cosmology operated on the principle that matter in the universe, while unevenly distributed, obeyed predictable statistical patterns. Clusters of galaxies formed where matter density was high, while voids appeared where it was low, but these voids were thought to be relatively small tens of millions of light-years wide, not hundreds. The scale of Kirshner's find was inconceivable, a hole so enormous that it seemed incompatible with the known age and physics of the universe. When the results were first presented, even experienced astronomers reacted with disbelief. How could such an empty region exist in a cosmos supposedly governed by gravitational attraction, where matter naturally clumps together over time? In those early days, skepticism ran high. Data from the redshift surveys suggested that, within this immense bubble, there were scarcely any galaxies, perhaps a few dozen scattered across a volume that should have contained thousands. At first glance, it appeared as if nature had violated its own rules. To grasp the magnitude of the void, one must remember that light, the fastest thing in existence, takes millions of years merely to cross between neighbouring galaxies. A region 300 million light-years across represents a vast gulf of time and distance, a realm so immense that human language strains to describe it. If a spacecraft could travel at the speed of light, it would need 300 million years just to journey from one edge of this cosmic cavity to the other. To put that in perspective, our species has existed for only a few 100,000 years, and our civilization for barely a few thousand. The Boötes Void is not merely large, it is practically eternal on human timescales. For Kirshner and his colleagues, realizing this was a moment of both awe and unease. The void was not just another data point, it was a message written across the fabric of space, suggesting that the universe was stranger and less uniform than anyone had dared to believe. As follow-up observations confirmed the existence of the Boötes Void, curiosity turned into fascination. The idea that the universe could contain such massive stretches of nothingness forced cosmologists to reconsider the very concept of structure. The traditional view held that galaxies trace a kind of cosmic web, a vast network of filaments and clusters separated by smaller gaps. Yet the Boötes Void was not a small gap. It was an abyss on a scale that dwarfed everything else. Its discovery was like stumbling upon an ocean in the middle of a desert, a revelation that transformed the way we see the cosmic landscape. For observers on Earth, the void occupies a region in the northern sky, within the boundaries of the constellation Boötes. Seen through telescopes, this area appears oddly unremarkable, a dark patch dotted with only a few faint smudges of light. But behind that unassuming appearance lies one of the universe's grandest mysteries. The sheer emptiness of the region makes it difficult to study. Without galaxies, there are few markers to measure or analyze. Still, astronomers have managed to map its rough shape and boundaries, revealing a roughly spherical expanse surrounded by clusters and superclusters of galaxies, massive walls enclosing an almost perfect bubble of darkness. It is not a black hole, not a region where matter collapses under gravity, but rather its opposite, a place where matter never gathered in the first place. When Kirshner's paper was finally published, it shook the astronomical community. The concept of a void on this scale implied that the early universe may have been far more chaotic and uneven than theories suggested. If regions like Boötes could exist, then the mechanisms of cosmic evolution, gravity, expansion, and dark energy needed to be re-examined. The Boötes Void became more than a curiosity. It became a symbol of the unknown, a silent challenge to cosmological orthodoxy. Even today, the image of that emptiness resonates beyond science. To contemplate it is to confront the limits of comprehension, to stand at the edge of existence and peer into a gulf where almost nothing resides. In that boundless stillness, amid the faint glow of a few lonely galaxies, one sees a reflection of both cosmic grandeur and existential fragility. The discovery of the Boötes Void marked not just a milestone in astronomy, but also a turning point in how humanity perceives its place in the vastness of space, a reminder that even in a universe filled with countless galaxies, the most profound revelations may come from the places where nothing seems to be. Try to imagine something 330 million light-years across. Not just a big number in a textbook, but an actual volume of space so vast, so profoundly empty, that it dwarfs even the grandest cosmic structures we know. That's the size of the Boötes Void, a spherical chasm in the universe so incomprehensibly huge that even light, travelling at the ultimate speed limit of the cosmos, takes 3.5 million centuries to cross from one side to the other. At 670 million miles per hour, a beam of light would reach the moon in just over a second, the sun in 8 minutes, and the edge of our galaxy in 100,000 years. But the Boötes Void? It would take that same beam 3,300 times longer just to make the journey across its breadth. This is not emptiness in the ordinary sense, it's emptiness stretched across a scale that mocks human perspective. For context, consider the Milky Way, our home galaxy. It contains between 200 and 400 billion stars, a shimmering whirlpool of matter, gas, and dark matter, spanning about 100,000 light-years. The Boötes Void could swallow our galaxy billions of times, not thousands, not millions, billions. If you placed galaxies like coins edge to edge across the void's diameter, you would need over 3,000 of them in a straight line just to span the width. It's not just an absence, it's a negation of presence on a cosmic level. A void so profound that it occupies roughly 2% of the entire observable universe. Let that sink in. 2% of everything we can detect, stars, galaxies, quasars, planets, and more, is taken up by this single, staggeringly empty bubble. Now think about how crowded the cosmos appears to us from Earth. When we look up at night, we see stars filling the sky. Telescopes reveal galaxies scattered like glitter across the deep field. And yet, within this monumental cavity, where by all calculations there should be tens of thousands of galaxies, we find only about 60. 60. A number so minuscule compared to the expectation that it defies probability, as though someone pressed delete on the cosmos and left behind a cosmic scar. According to the average density of galaxies throughout the universe, a volume the size of the Boötes Void should house no fewer than 10,000 galaxies. Some estimates even suggest numbers closer to 20,000. But observational surveys confirm only a few dozen, each separated from the next by distances so great that isolation becomes a kind of existential condition. To appreciate just how abnormal this is, imagine walking into the heart of Manhattan expecting a metropolis of millions, only to find 6 people wandering empty streets. The void doesn't merely lack content, it resists it. Normal regions of space feature galaxies separated by just a few million light-years. In the Boötes Void, the nearest galactic neighbour might be 10 million light-years away or more. This is isolation in the truest sense, where the fabric of space stretches so far between points of matter that interactions become improbable, even over eons. And what makes this more than just a scientific curiosity is the precision with which we can measure this void. Its volume has been calculated to span 236,000 cubic megaparsecs. A megaparsec is about 3.26 million light-years. Multiply that, and you're left with numbers so large they stop meaning anything. In miles, the void's volume would require a number with nearly 40 zeros. It's a size that crushes comprehension. Even more disconcerting is the fact that we see this void as it existed 700 million years ago. Light from its edge has been travelling toward us since a time when life on Earth was still crawling onto land. When vertebrates were only beginning to appear, that light has journeyed through unbroken darkness longer than complex organisms have walked the Earth. This means the void could have changed, grown, stretched, evolved, but to us, it is a fossil in motion, forever frozen in the past. And in that past, the void stands as a stark reminder of how uneven, how lumpy, how wildly inconsistent the universe truly is. It is the deepest form of emptiness we can measure, so extreme that it makes the already sparse stretches between galaxies look crowded by comparison. Imagine for a moment what it would feel like to exist inside that abyss. A lone astronaut drifting through its heart would be enveloped in silence and darkness so complete, so pervasive, that it would seem like the universe had ended. Every direction would stretch into blackness. No nearby stars, no constellations, only distant, faint glimmers perhaps millions of light years away. It would be the closest experience to non-existence one could have, while still remaining within the realm of the cosmos. Yet, despite its isolation, despite its seemingly impossible dimensions, the void exists. It is real, and its presence forces us to confront not only the structure of the universe, but the limits of our understanding. In a cosmos supposedly governed by gravity, expansion, and the distribution of matter, there lies this vast nothingness, calm, silent, and nearly untouched. The Boötes Void does not merely challenge our models, it whispers a deeper truth, that sometimes what's missing is more important than what's there, that within the vastness of all that is, the greatest mystery may lie in what isn't. When astronomers began calculating the number of galaxies that should exist inside the Boötes Void, their equations returned results that were almost absurd. According to every cosmological model, the average number density of galaxies in the known universe is roughly 1 galaxy per 10 million cubic light-years. That might sound sparse, but over cosmic distances it produces a remarkably uniform distribution galaxies, filling space like fine dust suspended in sunlight. Using that ratio, the volume of the Boötes Void should contain at least 10,000 galaxies. Yet when telescopes actually peered into that region, they found fewer than 60. 60 galaxies in a space where thousands should thrive is not a statistical fluctuation. It's an astronomical impossibility. The math didn't merely look wrong. It screamed that something fundamental was missing from our understanding of how the universe organizes itself. For the first time, scientists were forced to confront the idea that perhaps the cosmos is not as homogeneous as once believed. The Copernican principle, the assumption that no region of the universe is special, was suddenly under quiet assault. If one part of the universe could be this empty, what stopped others from being even more extreme? Could there exist places even more desolate, or conversely, regions so crowded with matter that gravity itself warps under the strain? The Boötes Void raised these questions not through speculation but through data cold, numerical, irrefutable. To make sense of the numbers, astronomers started comparing the void statistics with known cosmic structures. Typical voids found in surveys such as the CFA Redshift survey or later the Sloan Digital Sky Survey average between 30 and 50 million light-years in diameter. These smaller voids follow recognizable patterns. They're usually the result of gravitational clustering, the push and pull between regions of slightly different densities after the Big Bang. But the Boötes Void, over 6 times larger than any of these, could not be produced by ordinary cosmic evolution. It is the difference between a small pond drying under the sun and an entire ocean evaporating overnight. Even supercomputer simulations of large-scale structure formation, those that map billions of virtual particles evolving under gravity, fail to produce such a structure naturally. When the models are run forward from the early universe, voids appear, yes, but none remotely approach the scale or uniformity of Boötes. The numerical gap is too great to dismiss as coincidence. Some researchers suggested that the void might be the overlapping product of multiple smaller voids merging over time, like bubbles fusing into a larger sphere. In such a case, the internal galaxy count might appear artificially low because matter had been redistributed to the surrounding edges. Yet even this elegant idea falters when confronted with hard numbers. The galaxies that remain inside are not arranged chaotically, but appear aligned in a faint tube, a strange thread-like structure slicing through the emptiness. Their positions seem too orderly for random remnants of smaller voids. Others proposed that perhaps we are miscounting. Maybe faint galaxies lurk beyond the limits of our telescopes, but deep field surveys have since pushed that limit down to the faintest magnitudes imaginable, and still the emptiness holds. It's not that we cannot see the galaxies, it's that they aren't there. Statistically speaking, The odds of a region this large being so underpopulated are infinitesimal. A fluctuation of such magnitude in the cosmic matter field would require a variance so extreme that it contradicts the near-uniform temperature observed in the cosmic microwave background. That radiation relic light from the Big Bang tells us that matter density in the early universe varied by no more than 1 part in 100,000. For the Boötes Void to form naturally, it would have required a primordial fluctuation many orders of magnitude larger than that, an impossibility within standard inflationary theory. The numbers don't lie. Such a structure should not exist, and yet it does. These calculations forced cosmologists to re-examine every layer of their models. Perhaps dark energy or dark matter behaved differently in certain regions, amplifying expansion locally. Perhaps gravitational dynamics at vast scales diverge subtly from the laws that hold in galaxies. Or perhaps our notion of randomness itself was flawed. Maybe the universe contains deeper patterns, unseen symmetries guiding the placement of galaxies. The Boötes Void became a kind of statistical ghost story, an absence that haunted equations. It was not an error to be corrected, but an anomaly to be explained, one that made even the most seasoned physicists uneasy. The human mind is poorly equipped to comprehend such disproportionate numbers. To say that a region should contain 10,000 galaxies but holds only 60 is like discovering a continent where one expected an ocean. Each galaxy inside that space becomes an oddity, a survivor, a flicker of light in an ocean of absence. The void's density contrast defined as actual density minus average density, divided by average density, yields a figure close to 0.99, meaning it is 99% emptier than the cosmic average. That number alone conveys the absurdity. The Boötes Void is not just rare, it is nearly unique. Over time, these numerical impossibilities transformed the void from a curiosity into a central challenge of cosmology. Every attempt to reconcile the data, from inflationary fluctuations to modified gravity theories, runs up against the same stubborn fact. The void is too large, too empty, and too symmetrical. Its very existence implies that either the universe is far more heterogeneous than we imagine, or that something unknown has shaped it. The Boötes Void, when reduced to numbers, becomes more than a void. It becomes a mathematical rebellion, a silent rejection of our most trusted cosmic assumptions. And in that rebellion lies its fascination. Numbers, after all, are not supposed to lie, but here the numbers tell a story that feels impossible, and that impossibility is precisely what makes it real. When the first three-dimensional maps of the Boötes Void were completed, what astonished researchers most was not only its staggering size but its uncanny shape. It wasn't the amorphous, lumpy region one might expect from the chaotic forces of cosmic evolution. Instead, it was almost perfectly spherical, a geometry so neat, so balanced that it seemed deliberate. The universe, on the larger scales, is supposed to resemble a tangled web of filaments and knots, a sprawling network where matter gathers along strings of dark matter and energy. Voids appear naturally within this web, but they are typically irregular, stretched, and distorted by gravitational interactions with the denser regions around them. The Boötes Void, however, is eerily smooth, as if carved from space with mathematical precision. Its boundaries are sharp, its symmetry almost architectural, and its placement within the cosmic structure feels too exact to be coincidental. The more data astronomers collected, the more its geometry challenged the intuitive expectations of natural formation. If one could step outside the Milky Way and look down upon this region from a god's-eye view, the void would resemble a dark sphere embedded within a honeycomb of cosmic filaments, a hollow globe surrounded by walls of galaxies. Those walls are not uniform, they consist of 5 vast superclusters: Hercules, Corona Borealis, Boötes, Ursa Major, and Coma. Together they form a kind of cage, a cosmic shell encasing the emptiness. Each supercluster is made of tens of thousands of galaxies bound loosely by gravity, yet separated by immense gulfs of dark energy. From the perspective of a distant observer, it would look like a luminous ring of galactic fire encircling a black featureless center. This perfect juxtaposition, structure and void, fullness and absence, gives the Boötes region an almost poetic symmetry, one that has inspired as much philosophical wonder as scientific puzzlement. The boundaries of the void are not static. They seem to ripple faintly, responding to gravitational influences from nearby structures. But overall, the shape holds nearly spherical, slightly elongated along one axis, as though the universe itself took care to preserve its proportions. When computer simulations attempt to reproduce this kind of formation, the results are messy. They generate distorted bubbles, twisted by neighbouring mass concentrations, yet never produce the clean, simple geometry of Boötes. It is as though nature, in this one instance, decided to follow a rule of beauty instead of chaos. Some cosmologists find that troubling. Nature is supposed to be indifferent to aesthetics, yet here we find symmetry that borders on artistry. Measurements from redshift surveys and radio mapping confirm the void's contour extends roughly 330 million light-years in diameter and nearly equal in depth. Its surface marks an abrupt transition from near-total emptiness to dense galactic clusters. There is no gradual thinning of galaxies, no fuzzy gradient where matter tapers off. Instead, the change is almost binary. Inside, nothing. Outside, everything. This sharpness defies the soft edges expected from gravitational diffusion. It is as if some invisible boundary prevents galaxies from crossing into the void, like a bubble wall holding back the universe's substance. Whether that boundary is real defined by dark energy gradients, or cosmic topology, or merely an emergent statistical illusion, remains uncertain. The peculiar symmetry of the Boötes Void has led some scientists to describe it as the cosmic eye. In certain visualizations, it even appears like a pupil at the center of a galactic iris. Through it, astronomers can peer into the deepest reaches of intergalactic space, unclouded by intervening dust or stellar light. But the metaphor also fits symbolically. The void seems to stare back, a vast aperture of nothingness gazing into the universe. Its spherical shape makes it an ideal laboratory for studying how light travels through near-perfect vacuum. Photons passing through its center experience almost no scattering, allowing scientists to test the transparency of space itself. Yet, beyond its usefulness, the void's geometry continues to raise uncomfortable questions about why such perfection exists at all. In natural systems, symmetry usually points to powerful organizing principles. At the atomic level, symmetry defines stability. In living organisms, it arises from balance and efficiency. On cosmic scales, though, perfect symmetry is rare. Too many forces act over too much time. Galactic clusters pull unevenly, dark matter clumps unpredictably, and cosmic expansion stretches structures asymmetrically. And yet, against all odds, the Boötes Void holds its spherical form, serene and centered amid cosmic turbulence. Some theorists speculate that its shape could hint at ancient conditions in the early universe, perhaps a relic of an epoch when density variations were simpler, before gravitational chaos distorted them. Others entertain bolder ideas, that the void's geometry might be the fingerprint of exotic physics, maybe even the residue of a collision between different regions of the multiverse. The shape also carries psychological weight. There's something unsettling about perfection emerging from randomness, about order surfacing where none should be. The Boötes Void seems both natural and artificial at once, as if the universe momentarily paused its chaotic dance to sculpt a form of pure simplicity. Within its borders, the laws of probability appear suspended. The surrounding walls of galaxies frame it like the edges of a cathedral dome, each cluster standing at a respectful distance from the silent heart within. To human observers, it evokes both wonder and unease, a cosmic reminder that symmetry can be as mysterious as disorder. In the end, the shape of the Boötes Void remains an enigma wrapped in geometry. Its smoothness, its boundaries, its improbable roundness all defy the expectations of randomness. Whether it is a byproduct of natural processes we do not yet comprehend, or a signal of something deeper woven into the structure of space-time, the sphere stands as one of the universe's quiet masterpieces. In a cosmos defined by chaos, the Boötes Void whispers of precision. In its emptiness, it reveals the faintest outline of design, a perfect circle drawn on the vast canvas of infinity. At first glance, the Boötes Void appears almost completely empty, a cosmic gulf stripped of substance. Yet when astronomers examined its interior with more powerful instruments, they discovered something that deepened rather than diminished the mystery. Scattered within this colossal hollow is a faint thread-like formation of about 60 galaxies, all seemingly arranged along a narrow, elongated structure, a cosmic filament cutting through the heart of nothingness. It became known among researchers as the Tube of Galaxies, a name that conveys both its geometry and its peculiarity. Instead of being evenly dispersed across the void, these galaxies lie in a loose cylindrical band like beads strung along an invisible wire. Their distribution defies randomness, suggesting that some underlying gravitational or energetic process might have guided their placement. In a realm where almost nothing exists, these galaxies seem to cling together as if for survival, a fragile spine of light running through a sea of emptiness. Each of these 60 galaxies tells a story of isolation. In the crowded regions of the universe, galaxies live communally. They interact, collide, merge, and exchange gas and stars. Such encounters drive evolution, triggering bursts of star formation and shaping morphology over cosmic time. But in the Boötes Void, these processes stall. The galaxies there are effectively stranded, each separated from its nearest neighbour by distances that make gravitational interaction negligible. And yet, despite their seclusion, they appear remarkably intact. Observations show that many are spiral in shape, with well-defined disks and active star-forming regions. This is peculiar because spiral galaxies often depend on environmental nudges to maintain their structure. In denser regions, encounters compress gas and reignite star formation. In isolation, spirals are expected to fade, their gas depleted, their arms dissolving into featureless ellipses. But the Void's galaxies resist that fate, spinning serenely in the dark as though untouched by cosmic time. The alignment of these galaxies raises deeper questions. Why a tube? Why such order amid chaos? One possibility is that the tube represents a remnant filament of the cosmic web, a vestigial bridge that once connected larger structures before gravitational evolution hollowed out the surrounding space. If so, these galaxies may be survivors from an earlier epoch, left behind when the surrounding void expanded. Their existence could thus mark the fossilized remains of the universe's original scaffolding, a trace of the web's ancient architecture. Another theory suggests that the tube formed as smaller voids merged, compressing residual matter into a narrow corridor. When voids collide, their intersection can create thin filaments of higher density, a process somewhat akin to the ridges that form when soap bubbles press together. In this analogy, the Boötes Void would be the largest of the bubbles, and the Tube of Galaxies its final scar. To test these ideas, astronomers mapped the velocities of the galaxies within the tube. They expected to find chaotic motion, the random trajectories typical of underdense environments. Instead, they found coherence. The galaxies move in roughly parallel directions as though flowing along a shared gravitational current. This discovery complicates matters further. If the tube was simply the byproduct of random processes, the motion should appear disordered. Coherence implies structure, a lingering force shaping their behaviour even in near-total emptiness. But what force? Gravity alone seems insufficient at such scales, where mass is sparse and distances are immense. Some have proposed that dark matter may play a guiding role, forming an invisible spine along which the visible galaxies rest. If so, the tube could be the skeleton of a dark matter filament, a ghostly frame still binding luminous matter together long after ordinary forces have thinned away. From a visual standpoint, the image is haunting. Imagine a column of distant galaxies suspended in infinite night, each one a tiny whirlpool of stars glowing faintly against a black sea that stretches for hundreds of millions of light years in every direction. Between them lies nothing. No gas clouds, no dust, no intergalactic plasma, only the cold geometry of space itself. The light from these galaxies travels unimpeded for eons before reaching us, untouched by the scattering and absorption that plague denser regions. Observing them is like looking through the purest window in the cosmos. Their collective faintness, combined with the clarity of their isolation, gives the impression of a single, delicate thread of creation strung through a vacuum vast enough to swallow countless universes. Philosophically, the existence of this galactic tube inside such emptiness seems to capture the essence of cosmic paradox. It is both presence and absence, chaos and order, persistence and fragility. The tube demonstrates that even within profound nothingness, structure finds a way to survive. The laws of physics, indifferent and relentless, still produce symmetry and coherence where none should be possible. In that sense, the Boötes Void doesn't merely illustrate the absence of matter, it highlights the resilience of form. Life, too, follows similar patterns. Islands of order emerging against impossible odds in a surrounding sea of entropy. For cosmologists, this narrow chain of galaxies offers a crucial clue. If they can understand how such a filament persists inside the largest void known, they may unlock new insights into how dark matter and dark energy sculpt the universe's scaffolding. The tube could be a remnant signal, a subtle fingerprint left by the interplay between the visible and the invisible. Every galaxy within it is a marker, a coordinate in a grand equation still unsolved. The Boötes Void, for all its emptiness, may thus contain one of the most eloquent testimonies to the universe's underlying unity, a silent proof that even in the most forsaken places, the geometry of creation endures. In the early attempts to make sense of the Boötes Void's enormous emptiness, cosmologists turned to an idea both simple and elegant, the so-called soap bubble hypothesis. This model proposed that the universe on its largest scales resembles a foamy structure composed of countless bubbles of low-density regions, each bordered by thin filaments and clusters of galaxies. Just as soap bubbles merge into larger ones over time, smaller voids in the cosmic web might coalesce into supervoids like Boötes. The concept felt intuitive. In the aftermath of the Big Bang, matter did not spread evenly, but clumped together due to tiny quantum fluctuations. Denser areas became the seeds of galaxies and clusters, while underdense regions expanded faster, evacuating matter outward. Over billions of years, these expanding voids would collide, merge, and leave behind vast pockets of nothingness separated by filaments of galaxies, precisely the walls that now encircle the Boötes Void. The model was comforting in its familiarity. It explained the universe's filamentary nature without invoking exotic physics. Yet when applied to the scale of Boötes, the metaphor began to crack. Computer simulations of large-scale structure formation were run repeatedly in the decades following Kirshner's discovery. They began with the primordial density variations measured from the cosmic microwave background ripples, no greater than 1 part in 100,000ers, and let gravity and expansion evolve them over cosmic time. The results reliably produced networks of filaments, clusters, and voids, confirming the foam-like texture of space. But none of the simulations could generate a void as immense as Boötes within the universe's age constraints. Smaller voids, yes, plenty of them, but nothing approaching 300 million light-years in diameter. The bubbles in the model simply didn't merge fast enough. Even when scientists artificially boosted the rate of merging, the resulting supervoids were distorted, irregular, and lacked the smooth symmetry observed in Boötes. The numbers refused to cooperate. To produce such a colossal hollow naturally, the universe would have needed more time or more extreme initial fluctuations than the Big Bang appears to have allowed. Despite its shortcomings, the soap bubble hypothesis retains a powerful explanatory charm. The image of a frothy universe, a cosmic foam where galaxies line the surfaces of expanding bubbles, captures the structure of the cosmos with poetic accuracy. In this vision, our galaxy itself resides not at the center of anything, but along the edge of one of countless bubbles, suspended between neighboring voids like an atom in a vast lattice. The Boötes Void would then represent one of the largest cells in this structure, perhaps the endpoint of multiple mergers over cosmic epochs. If that is true, the void's smoothness may be the result of equilibrium, the natural roundness that emerges when many smaller bubbles fuse and settle into a single stable configuration. Even so, questions remain. How could such equilibrium arise when gravity, expansion, and dark energy pull the universe in conflicting directions? Why does the Boötes Void appear almost perfectly spherical, while smaller voids are twisted and asymmetric? One possibility is that the void's boundaries are shaped by surrounding superclusters, whose combined gravitational pull maintains balance. The 5 great walls that ring the void, Hercules, Corona Borealis, Coma, Boötes, and Ursa Major, could act like cosmic membranes, pressing evenly against the hollow center. Their mutual tension might give rise to the observed symmetry. Another interpretation is that dark energy, which drives the acceleration of cosmic expansion, acts differently inside vast underdense regions. Because there is less matter within the void, the repulsive influence of dark energy could dominate more strongly there, causing the space inside to stretch more rapidly and smooth itself into a perfect sphere. If true, Boötes might be a natural demonstration of dark energy's local effects, an enormous silent expansion balloon within the cosmic web. Still, even this refined model does not explain everything. The soap bubble analogy falters when one considers the interior galaxies, especially the mysterious tube structure slicing through the void. If smaller voids merge to form Boötes, their collision boundaries should have left behind chaotic filaments of leftover matter. Instead, we find a single, coherent band of galaxies, arranged with almost deliberate precision. Nor does the bubble model account for the time paradox. If such a void requires longer than the universe's current age to form, then either our understanding of cosmic evolution is incomplete, or the void is older than the cosmos itself in its current form. That contradiction lies at the heart of why the Boötes Void continues to puzzle even the most sophisticated simulations. The persistence of the soap bubble hypothesis, despite these discrepancies, speaks to the human need for metaphors that make sense of the incomprehensible. The model endures not because it fully explains the data, but because it offers a visual and conceptual framework, a way to imagine the unimaginable. When astronomers picture the universe as a sea of bubbles, they can at least conceive of how something like Boötes might emerge, even if the details elude them. It is the same impulse that once drove early scientists to describe atoms as miniature solar systems or galaxies as cosmic islands. Such analogies are not literal truth, but bridges of comprehension, scaffolding that holds our curiosity while we search for deeper answers. Perhaps, in the end, the Boötes Void is both a triumph and a failure of the bubble model, a structure that both validates and transcends it. The void shows that the universe does behave like a foam, yet also reminds us that reality often refuses to conform to our neatest theories. The Boötes Void may indeed be the ultimate bubble, the one that grew too large, too perfect, and too improbable to fit inside our equations. And like all bubbles, it hints at fragility, a whisper that even on the grander scale, the fabric of the cosmos is delicate, its boundaries fleeting, its emptiness both beautiful and profoundly mysterious. Among the many enigmas surrounding the Boötes Void, perhaps none is as disturbing as the problem of time. When scientists began to calculate how long it would take for a region of such magnitude to form naturally through the normal gravitational evolution of the universe, they found themselves confronting an impossible conclusion. There simply hasn't been enough time since the Big Bang for it to exist. The standard cosmological model tells us that the universe is roughly 13.8 billion years old, and that galaxies and large-scale structures began taking shape around 1 billion years after its birth. Gravity, slow and patient, pulls matter into clusters and superclusters, while simultaneously leaving other regions underdense. Over billions of years, these underdense zones expand faster than their surroundings, gradually becoming voids. But when the numbers are applied to Boötes, the math fails spectacularly. Even under the most optimistic conditions, the formation of a void 330 million light-years wide would require nearly twice the current age of the universe. This contradiction, often referred to as the Boötes timescale paradox, forces cosmologists into uncomfortable territory. If the void could not have formed within the known lifetime of the universe, then either our timeline is incomplete, our physics inadequate, or the void represents something fundamentally different from any other structure we know. In the 1980s, when this problem was first recognized, some scientists speculated that the Boötes Void might be a relic from an earlier cosmic epoch, perhaps a leftover scar from a pre-Big Bang phase, or a pocket of space-time that evolved independently before the universe as we know it began. Others suggested that the void might have been stretched to its current size by an early burst of inflation stronger or more prolonged than the one predicted by standard theory. Yet both explanations carry difficulties. They require rewriting parts of cosmological history that have otherwise been confirmed by observation. More conservative physicists tried to reconcile the timescale paradox within existing models. They argued that while gravitational collapse shapes most large-scale structures, other forces, particularly dark energy, might accelerate the evacuation of matter from certain regions, making them expand faster than expected. In this view, the Boötes Void is not older than the universe, but is expanding more rapidly than average, giving it an apparent age older than the cosmos itself. The problem is that dark energy, as currently measured, acts uniformly across space. If its influence was significantly stronger inside the void, we would expect to observe measurable distortions in the cosmic microwave background, subtle gravitational lensing effects, or shifts in the redshift of galaxies at its boundary. Yet none of these indicators appear. The void remains eerily silent, expanding neither faster nor slower in any measurable way, simply existing as if exempt from the normal pace of cosmic time. Another approach reframes the question altogether. Perhaps some argue the void did not need to form in the traditional sense. Instead, it might have been an initial condition, a region that was underdense from the very beginning. Tiny variations in the early universe could have produced rare but extreme pockets of low density, which later inflated into massive cavities. In this scenario, the Boötes Void is not an evolved feature, but a primordial scar, a trace of initial asymmetry frozen into the universe's earliest moments. That idea aligns loosely with the inflationary model, which predicts quantum fluctuations of all magnitudes. However, for Boötes to arise this way, the fluctuation responsible would have needed to be improbably large, so large that the statistical odds are vanishingly small. The universe, in other words, would have had to be extremely lucky or unlucky, depending on one's perspective, to produce such an outlier. The time problem also manifests in the behavior of the galaxies within and around the void. Computer simulations suggest that the evacuation of matter from such a massive region should take billions of years and leave behind significant turbulence. Yet observations show that the galaxies near the void's boundary move smoothly, with velocities that align perfectly with the surrounding expansion of the universe. There is no sign of violent disruption, no trace of the gravitational chaos that should accompany the rapid formation of such a cavity. The galaxies within the void. The lonely few that populate its central tube also display no signs of recent upheaval. Their stars rotate calmly, their gas clouds drift undisturbed. It is as though they have always been alone, as though the void's stillness predates them entirely. This temporal dissonance has led some theorists to propose an even stranger interpretation. Perhaps time itself flows differently inside the void. General relativity allows for variations in the passage of time depending on gravitational potential. In high-density regions where gravity is strong, time runs slightly slower. In low-density regions where gravity is weak, time runs a bit faster. Could the Boötes Void, being one of the emptiest places in the universe, represent an extreme case of this phenomenon, a vast domain where time has raced ahead of the surrounding cosmos? If that were true, the void could appear older simply because it has experienced more time than the denser regions around it. The difference would be minute on human scales, but could accumulate into billions of years across cosmic distances. However, testing such a hypothesis is nearly impossible. We have no way to measure time directly across light years, only its traces in the motion of matter and the redshift of light. For now, it remains speculation, an elegant possibility, suspended between physics and philosophy. What the time problem ultimately reveals is the fragility of our cosmic chronology. The universe, we believe, has a story with a beginning, a middle, and perhaps an end. But the Boötes Void stands as a challenge to that narrative. It suggests that time may not flow uniformly, that structure formation may not follow a single rhythm, and that some regions of space may bear witness to epochs we cannot yet fathom. Whether it is a relic from before time as we know it, or simply an extreme manifestation of known laws, the void reminds us that cosmic history is far from settled. Its existence is a quiet rebellion against the clockwork of the universe, a silent region where time itself seems to have lost its bearings. When astronomers first confronted the Boötes Void, one of the earliest ideas proposed to explain its vastness centered on a mysterious component of the cosmos that was, at the time, only beginning to enter scientific conversation: dark energy. This invisible force, believed to permeate all of space, drives the acceleration of the universe's expansion. If dark energy could stretch galaxies apart on a cosmic scale, perhaps it could also carve out enormous cavities within the cosmic web. The reasoning was straightforward enough. Regions with slightly lower matter density might experience a stronger local effect of dark energy, causing them to expand faster than denser surroundings. Over billions of years, such regions could grow disproportionately large, pushing galaxies outward and leaving behind an emptiness like the Boötes Void. It was an elegant hypothesis, one that promised to unite two of cosmology's greatest mysteries, voids and dark energy, under a single explanatory umbrella. Yet, Like so many ideas that confront the Boötes anomaly, this one soon ran into problems of its own. Dark energy, according to current observations, appears to act uniformly throughout the universe. Measurements of distant supernova, the cosmic microwave background and large-scale galaxy surveys all point to a consistent value for the cosmological constant, the mathematical term Einstein introduced to describe this repulsive energy. If dark energy behaves the same everywhere, it cannot be stronger inside the Boötes Void than it is elsewhere. That means the void's immense expansion cannot be attributed to any local enhancement of this force. The data suggest that dark energy's contribution to the universe's structure is subtle and slow, significant only over cosmic scales comparable to the universe itself. Its effect within a single void, even one as enormous as Boötes, would be negligible. And yet the Boötes Void exists, mocking the limits of uniformity and hinting that our understanding of dark energy may still be incomplete. Some cosmologists have suggested that dark energy might not be constant after all. Perhaps it fluctuates slightly over time or across space, its density varying like ripples on an unseen ocean. If so, then regions of slightly higher dark energy concentration could expand faster, creating supervoids, while regions of lower concentration might contract into clusters and superclusters. This dynamic form of dark energy, sometimes called quintessence, could, in theory, produce structures like Boötes. In such models, the void becomes a local exaggeration of the universe's global acceleration, a place where the cosmic repulsion gained a temporary advantage over gravity. But so far, no observation has confirmed any variation in dark energy's distribution or strength. The cosmological constant remains, frustratingly, constant. Every attempt to detect deviations through gravitational lensing, baryon acoustic oscillations, or galaxy clustering has yielded the same result: smoothness. The cosmos expands evenly, without apparent bias. Still, the temptation to link the Boötes Void to dark energy persists. After all, both represent expressions of cosmic emptiness. Both involve the interplay between gravity and expansion, and both hint at a deeper layer of physics beneath the observable universe. One of the more provocative suggestions in recent years posits that voids like Boötes could act as magnifying glasses for dark energy's behavior. Because they are nearly devoid of matter, voids are less contaminated by gravitational complexity, making them ideal laboratories for studying how space itself stretches. By measuring how light from distant galaxies bends, redshifts, or dims as it passes through these emptier regions, astronomers hope to detect subtle differences that might betray the fingerprints of dark energy at work. If any part of the cosmos could reveal variations in the expansion rate, it would be here, in these silent expanses where gravity's grip is weakest. However, direct evidence remains elusive. When the cosmic microwave background, the afterglow of the Big Bang, is examined through the Boötes region, it shows no significant deviation from the surrounding sky. This absence of anomaly is both reassuring and perplexing. It suggests that the void's presence doesn't distort spacetime enough to alter the flow of photons across it. In other words, the Boötes Void behaves as though it is simply an oversized empty pocket in an otherwise uniform universe, and yet the sheer improbability of its size implies that some unknown mechanism must have exaggerated its formation beyond ordinary gravitational processes. Could it be that dark energy, while globally constant, interacts with matter and dark matter in ways we do not yet understand? Perhaps it subtly amplifies pre-existing voids, smoothing and expanding them over cosmic time. The tension between theory and observation has turned the Boötes Void into a testing ground for the limits of cosmology. If dark energy is not perfectly uniform, then its subtle variations could explain not only the void scale, but also the distribution of galaxies across the entire cosmic web. On the other hand, if dark energy truly is constant, then the Boötes Void must owe its existence to something entirely different, perhaps an anomaly imprinted in the very fabric of spacetime at the universe's birth. Either answer would revolutionize our understanding of cosmic evolution. What makes the link between dark energy and the Boötes Void so compelling is that both challenge human intuition about balance. The universe we inhabit is not merely expanding, it is accelerating in its expansion. Space itself grows more quickly with time, stretching the bonds between galaxies. The Boötes Void might simply be a preview of what the distant future will bring, a universe increasingly dominated by emptiness, where isolated galaxies drift apart until the night sky fades into black. In that sense, the void is not an aberration, but a prophecy, a glimpse into the ultimate fate of all structure. As dark energy continues its quiet work, every galaxy will eventually become a lonely island, every cluster surrounded by its own private Boötes Void. The emptiness we see now may one day become the rule rather than the exception. For now, however, the mystery remains unresolved. The Boötes Void stands as a reminder that even our most sophisticated theories, dark energy, cosmic inflation, general relativity, are only approximations of a reality far deeper than we can yet model. Whether it is a relic of early cosmic fluctuations or a manifestation of dark energy's hidden complexity, the void speaks a single truth: that expansion, not matter, is the universe's defining act, and within that act, silence reigns. When astronomers describe the Boötes Void as one of the emptiest places in the known universe, the statement is not a metaphor, it is a physical fact. The space inside that colossal bubble approaches what physicists call a perfect vacuum, a condition so rare that even our most advanced laboratories on Earth cannot reproduce it. In interstellar space, between stars within a galaxy, one might find a few atoms per cubic centimetre. In intergalactic space, that number drops dramatically to perhaps 1 atom per cubic metre. Inside the Boötes Void, the density is orders of magnitude lower still, so close to nothing that for all practical purposes it is nothing. If you could somehow float within it, you would be surrounded by a silence deeper than thought, a darkness untouched by starlight, and a stillness unbroken by matter or radiation. It is the nearest the universe comes to absolute emptiness, a pocket of pure void existing within a cosmos that otherwise hums with the faint background of creation. To understand just how empty that is, imagine a cube of space the size of our entire solar system, stretching from the Sun to Pluto and beyond. In most regions of the universe, that cube would contain countless dust grains, hydrogen atoms, and streams of cosmic rays. Inside the Boötes Void, that same cube might hold a single lonely proton, or perhaps nothing at all. On a human scale, the difference between almost empty and completely empty feels trivial, but on a cosmic scale, that difference is profound. The near-total absence of matter changes how space behaves, how light travels, and how time itself flows. In the void's interior, gravity's influence is negligible. There are no magnetic fields, no plasma filaments, no dense intergalactic medium-only the bare geometry of space-time, stretching effortlessly across hundreds of millions of light-years. This near-perfect vacuum turns the Boötes Void into a natural laboratory for physics. Because there is so little material to interfere, it offers a pristine environment for studying the fundamental properties of space itself. Photons that enter the void travel unimpeded for unimaginable distances. They do not scatter off gas or dust. They do not bend around stars or pass through nebulae. Their journey becomes a direct experiment in the transparency of the universe. Similarly, neutrinos, those ghostly, nearly massless particles that stream from supernovae and stars, can cross the void undisturbed. If detectors could one day measure the faint flux of such particles passing through, the Boötes Void would serve as an unparalleled window into distant cosmic events. In this sense, emptiness becomes a tool for discovery, an absence that reveals more than presence ever could. The purity of this vacuum also raises philosophical questions about the nature of nothingness. Is a void truly empty if space itself has structure? Quantum physics tells us that even the emptiest region of space is never truly blank. It seethes with virtual particles, momentary fluctuations that blink into and out of existence, too quickly to be observed directly. These quantum ghosts give the vacuum an energy density known as zero-point energy. In the Boötes Void, the absence of matter allows these quantum effects to exist in near isolation, undisturbed by ordinary forces. Paradoxically, that means the void may contain as much energy in the form of quantum fluctuations as an entire cluster of galaxies does in visible matter. It is an emptiness that hides fullness, a silence humming with invisible resonance. If an observer could somehow stand inside the Boötes Void, suspended between its few scattered galaxies, they would see almost nothing at all. The sky would not blaze with stars as it does from Earth. Even with perfect eyesight, they might count only a few faint smudges of light, each one a galaxy tens of millions of light-years away. The Milky Way, with its brilliant arms and crowded starfields, would seem impossibly foreign compared to such isolation. In every direction would lie the same darkness, cold and eternal, broken only by the faint background glow of the cosmic microwave radiation, the afterimage of the Big Bang itself. The temperature of that radiation, about 2.7 Kelvin above absolute zero, would define the environment entirely. There would be no heat, no sound, no air, no resistance of any kind, only the lingering echo of the universe's first light washing through an ocean of nothing. This extreme emptiness challenges not only our physics but also our intuition. Humans evolved in a world of density air to breathe, ground to stand on, matter pressing on every side. Even the vacuum of space near Earth, filled with solar wind and micrometeorites, is busy by comparison. The Boötes Void is a place beyond experience, where the concept of distance loses meaning because there are no nearby reference points. It is the closest thing to pure absence that the universe can produce, and yet it exists within a universe that refuses to be truly void. There is still gravity, still space-time curvature, still the hum of the quantum field that prevents absolute nothingness from ever being reached. For cosmologists, the near-perfect vacuum of the Boötes Void offers a chance to probe the universe's deepest assumptions. Why does space, even when emptied of matter, still have structure and energy? Why can it stretch and curve as if it were something rather than nothing? The void invites us to reconsider the very definition of existence. Perhaps, on the grandest scale, emptiness is not the opposite of being but another expression of it, a silent counterpart to matter's clamour. In that sense, the Boötes Void may represent not absence but equilibrium, the universe balancing its fullness with a necessary void, ensuring that creation has room to unfold. What appears to be a hole in the fabric of reality might instead be the fabric itself laid bare, stripped of adornment, revealing that even nothing is something after all. In a universe defined by the dance of light and matter, the Boötes Void stands as a stage almost devoid of performers, yet it is precisely this emptiness that turns it into one of the most perfect conduits for light and particles ever known. In the dense regions of the cosmos clusters, filaments, and galaxies light rarely travels undisturbed. It is absorbed by dust, bent by gravity, scattered by plasma, and redshifted by motion. Every photon carries the scars of its journey, the fingerprints of the matter it has touched. Inside the Boötes Void, however, those fingerprints fade away. Photons entering its vast expanse travel through near-absolute vacuum, crossing hundreds of millions of light-years without encountering a single obstacle. It is as if the void is a cosmic hallway where light can walk in silence, preserving the message it carried from the dawn of time. For astronomers, this makes the Boötes Void not just an absence, but a rare clarity, an intergalactic mirror reflecting the unfiltered behavior of space itself. The transparency of the void allows light to act as a kind of messenger, revealing properties of the universe that are normally hidden behind the interference of matter. When radiation from distant quasars passes through the Boötes region, it does so without being distorted by the intervening medium. This means that by analysing the spectra of such light, scientists can measure the universe's true expansion rate, its precise curvature, and even the potential influence of dark energy without the noise of gravitational clutter. The void is a natural lens, not because it bends light, but because it doesn't. It offers a pure baseline, a section of space where photons tell the truth. But light is not the only traveller through this emptiness. Neutrinos, the ghost particles of the cosmos, stream endlessly through everything from stars to planets to the vacuum between galaxies. They rarely interact with matter, slipping through it as if it were transparent. Yet in most regions of space, even neutrinos encounter occasional disruptions. Atomic nuclei, electromagnetic fields, gravitational wells. Inside the Boötes Void, those disruptions are almost non-existent. The neutrino, that elusive witness of the universe's birth, can move through this darkness for billions of light-years without ever colliding with another particle. For this reason, physicists often imagine the Boötes Void as the ultimate neutrino laboratory, a cosmic detector in reverse place where interference is so minimal that the faint whisper of the universe's most subtle particles could, in principle, be observed with unprecedented precision. If we could place detectors on opposite sides of the void, synchronized in time, they could watch as particles born in distant supernovae glide silently through the emptiness. By measuring the slight differences in arrival times, scientists could infer properties about neutrino mass, oscillation, and velocity keys to understanding one of the universe's most enduring mysteries. But such experiments remain theoretical dreams. The technology to observe neutrinos across hundreds of millions of light-years is far beyond current capabilities. For now, the Boötes Void remains a symbol rather than a laboratory, a reminder of what science might one day measure when its reach catches up to its imagination. The silence of light within the void carries philosophical weight as well. In most of the universe, light reveals structure, it outlines galaxies, illuminates nebulae, and reflects off matter. But in the Boötes Void, light moves through nothing and reveals nothing. It becomes invisible not because it is absent, but because there is nothing for it to touch, nothing to echo against. It is the purest form of light, unreflected, unscattered, and unobserved. The photons travelling through that darkness are witnesses without audience, information without interpretation. They will continue their flight for hundreds of millions of years, some perhaps never encountering matter again before the end of the universe. In that way, the Boötes Void is a kind of cosmic library, filled not with books but with unbroken trajectories, stories of creation written in the motion of light, preserved perfectly yet unread. The lack of scattering also means that the cosmic microwave background, the faint relic radiation of the Big Bang, passes through the Boötes Void with unaltered purity. This offers cosmologists an extraordinary opportunity to use the void as a window through which to observe the early universe with minimal distortion. When mapped, the microwave background across the Boötes region appears almost pristine. No interference, no temperature anomalies, no gravitational lensing strong enough to warp its patterns. This suggests that the void is as close as nature allows to perfect transparency. Space there behaves like glass, flawless, invisible, infinite. Even time seems to behave differently in such emptiness. Light travelling through dense regions of space slows fractionally due to gravitational effects. In the Boötes Void, freed from the tug of matter, photons travel along nearly perfect geodesics, the straightest possible paths through space-time. It is as if light there experiences the universe in its purest form, untouched by distortion, moving effortlessly through geometry itself. The void is not merely an empty space, it is a calibration point for reality, a benchmark against which all other motion and measurement might be compared. In contemplating this, one is reminded that light and neutrinos are storytellers of the cosmos, carrying news from places we will never reach. The Boötes Void, then, is both silence and scripture, a space where those stories are written without interruption. If galaxies are the sentences of the universe, the void is the blank page between them, the pause that gives meaning to what is said. It is a place where light remains pure, where the cosmos reveals its simplest truth, that even in utter emptiness, motion endures, and through that motion, the universe remembers itself. Among the 60 or so galaxies adrift within the vast interior of the Boötes Void, one stands out as a symbol of cosmic solitude. Catalogued as MCG G020115, it is sometimes called the loneliest galaxy in the universe. This spiral system floats near the heart of the void, hundreds of millions of light-years from its nearest substantial neighbour. To human imagination, it is an island of light adrift in a sea of black infinity, a solitary ember burning quietly in the coldest, emptiest place known to science. If the Boötes Void embodies the absence of everything, then this galaxy embodies endurance, the persistence of structure and motion where no structure should survive. For astronomers, MCG plus 01, 02, 01 theme is both a scientific anomaly and a poetic metaphor, a reminder that even in the deepest emptiness, the universe refuses to extinguish its lights completely. When telescopes first captured its faint spiral outline, astronomers were surprised not by what they saw, but by what they didn't. The galaxy looked normal, disarmingly normal. It possessed a defined disk, winding arms, and a bright core glowing with clusters of young stars. In every respect, it resembled a typical mid-sized spiral such as the Milky Way, though somewhat smaller and dimmer. but its surroundings defied reason. In a space 330 million light-years across, MCG plus 01, 02 and 015 was almost completely alone. There were no neighbouring galaxies to tug at its arms, no clusters to exchange matter with, no intergalactic gas clouds to replenish its star-forming regions. Yet paradoxically, it continued to generate new stars, suggesting a reservoir of gas that had somehow remained unconsumed across billions of years. How could a galaxy thrive in such isolation? What mechanism allowed it to resist entropy in a place where even gravity seemed to have withdrawn? To understand its significance, it helps to recall how galaxies evolve. In populated regions of the cosmos, galaxies are constantly shaped by interaction gravitational encounters, mergers, and tidal distortions that fuel bursts of star formation. Isolated galaxies, deprived of such stimulation, should grow old and quiescent. Their gas clouds collapse, their stars burn out, and their disks fade into dim ellipses. MCG plus 01, 02, 015, however, appears youthful. Its colour indicates ongoing star formation. Its structure is undisturbed, symmetrical, and serene. It rotates gracefully, its spiral arms still lined with blue stars and nebular light. For this reason, it has become a paradoxical emblem, a galaxy that lives in defiance of both its environment and our models of galactic evolution. Some researchers have proposed that its survival owes to the peculiar physics of voids themselves. Because there are no nearby gravitational giants to disturb it, MCG plus 02 may have evolved slowly, almost timelessly, maintaining stability for billions of years. In crowded regions, collisions and tidal forces accelerate galactic aging, tearing apart delicate spiral arms. In the void, by contrast, the absence of such interactions may preserve structure indefinitely. The galaxy's gas reserves, never stripped or compressed, could continue fueling modest star formation at a sustainable rate. In this sense, the void might act as a kind of cosmic cradle, harsh and silent but protective. The galaxy within it becomes a hermit, living on its own resources, untouched by the violence that shapes most of the universe. Others suggest a more dramatic origin. Perhaps MCG plus 01 lost 2015 was not born inside the void but fell into it. As the surrounding walls of galaxies expanded outward, gravitational dynamics might have flung this single galaxy inward, leaving it stranded in the growing emptiness. If so, it would be a kind of exile, a wanderer thrown from its birthplace into solitude. Over hundreds of millions of years, the void expanded faster than the galaxy could escape, trapping it in a permanent cosmic desert. This scenario evokes an almost tragic imagery. A luminous voyager adrift in a sea that grows endlessly larger around it, moving farther from all others until even the concept of direction loses meaning. For an observer living inside MCG plus 01, 02, 015, the night sky would be unrecognizable. From Earth, the Milky Way glows with thousands of nearby stars, and beyond it, telescopes reveal billions of galaxies. From the Boötes Void, the heavens would be almost empty. Only a few faint galaxies would appear as dim smudges scattered across the dark, perhaps so distant that they would remain fixed points for all eternity. There would be no grand panorama of cosmic light, only the faint whisper of isolation stretching in every direction. Civilizations, if they ever arose there, might never suspect they lived in a universe filled with galaxies. Their instruments would detect only their own galaxy and the cosmic microwave background, a faint uniform glow that might appear to them as the echo of creation itself. Their philosophers would look outward and see infinity, believing themselves utterly alone. From a scientific perspective, MCG plus 01, 02 stu, 015 offers rare insight into how galaxies function without external influence. Its isolation makes it a perfect test case for the intrinsic processes of galactic evolution, free from the distortions of neighbouring interactions. By studying its rotation curves, metallicity, and stellar populations, astronomers can measure how a galaxy ages in solitude. Early data suggest that it rotates slightly faster than predicted, implying a massive dark matter halo that stabilizes its structure. Its stars show surprisingly high metallicity, indicating that star formation has been continuous rather than sporadic. These clues paint a picture of slow, steady life, an equilibrium reached not through abundance but through perfect isolation. Philosophically, MCG plus 01 02 suas 01 ftiv occupies a strange middle ground between despair and endurance. It is a testament to persistence, a living contradiction that turns emptiness into sanctuary. While most galaxies exist as social creatures, bound in communities, this one survives as a solitary witness to the universe's vast indifference. It glows not because it must, but because it can. Its light crosses the dark, reaching us after hundreds of millions of years, a message that might as well read, "I am still here." Within that faint spiral, surrounded by silence, lies perhaps the most profound truth of all, that even in the deepest void, creation finds a way to continue, quietly, defiantly, eternally. Imagine a civilization born inside the Boötes Void. From their earliest myths to their most advanced sciences, their entire worldview would be shaped by isolation. When they looked up at their night sky, they would not see a dome sprinkled with billions of stars and galaxies. They would see only darkness, vast, unbroken darkness, punctuated by a few faint smudges of light. Their own galaxy would dominate the heavens, a magnificent spiral hanging across the void, but beyond it there would be almost nothing. The idea of a universe filled with galaxies would not exist for them, because there would be no evidence of such a universe. To those hypothetical beings, their galaxy might appear to be all that is, suspended in an infinite black sea without neighbours, without boundaries, without purpose beyond itself. In the Boötes Void, the cosmos would appear finite and self-contained, a solitary island in an endless ocean of nothing. From the perspective of such inhabitants, the concept of cosmology would be fundamentally different from ours. On Earth, astronomers look outward and see patterns clusters, filaments, superclusters, an intricate web of galaxies stretching across the universe. For a civilization in the void, no such patterns would exist. Even with powerful telescopes, they might detect a handful of faint galaxies at the edge of visibility, but these would be so distant and dim that they would appear almost like background noise. Their redshifts would be enormous, implying speeds so great that such galaxies would seem to be fleeing faster than comprehension allows. Without the context of a rich cosmic environment, these distant objects might be dismissed as anomalies or illusions. In that darkness, they would build their cosmology around themselves, assuming that their lone galaxy was the totality of existence. Their philosophy would reflect that solitude. On Earth, human beings often feel small when confronted with the scale of the universe. But for those who live in the Boötes Void, smallness would not be the issue, loneliness would. The idea that they were utterly alone would not be terrifying, but natural, woven into the foundation of their thinking. Their religions, if they developed them, might focus on inward connection rather than cosmic unity. Their gods would not dwell in distant galaxies or other worlds, but in the quiet spaces between stars, in the silence that surrounds their existence. Their creation myths might speak not of a grand explosion filling the heavens, but of a single spark igniting within infinite nothing, a mirror of their own condition. To live in the Boötes Void would be to exist in perpetual introspection, to turn the search for meaning inward because the outer world offers none. Technologically, such a civilization would face unique challenges. Without nearby galaxies to observe, their understanding of astrophysics would develop slowly. They might never deduce the true scale of the universe, because there would be no reference points to measure against. The cosmic microwave background would still exist, faintly glowing in every direction, but it would appear almost featureless, a soft whisper of radiation that might be dismissed as a property of space itself, rather than the residue of a universal beginning. Without a crowded sky to inspire questions about motion, gravity, and structure, their scientific revolutions might emerge centuries or millennia later than ours. And yet, once they began to grasp their situation, their discoveries would strike with devastating force. The realization that their galaxy was adrift in a void 330 million light-years wide, that the nearest clusters lay unimaginably far away, would shake their sense of place to its core. To learn that they were not the centre of the universe but rather a single light in a sea of black. Such a revelation could transform their civilization forever. The psychology of that existence is difficult to imagine. On Earth, we're comforted by abundance. Stars, planets, galaxies, life. The night sky reassures us that we are part of something vast and interconnected. For a species in the Boötes Void, the opposite would be true. Their sky would teach them isolation. Even if they built spacecraft capable of travelling at relativistic speeds, they would find no destinations. Every mission would end in darkness. Every probe would drift endlessly, its signals fading as it plunged deeper into the void. Exploration, which on Earth expands horizons, would only confirm how small and alone they truly were. Their greatest achievements might not be journeys outward, but inward, mapping their own minds, mastering their own energy, building artificial worlds to fill the silence that space denies. And yet, despite the loneliness, there might also be freedom. In that emptiness, unshackled from cosmic neighbours, their galaxy would be untouched by external gravity or collision. Their stars would evolve in peace, their planetary systems would orbit undisturbed for billions of years. Catastrophic mergers and gamma-ray bursts from nearby galaxies' threats that haunt denser regions would be rare or non-existent. Life in the void would be safe in a way the crowded universe can never be. Perhaps that tranquility would shape their values. Instead of fearing the darkness, they might learn to revere it. They would look upon the infinite black not as absence but as sanctuary, a cosmic womb holding their galaxy in silent embrace. In the end, the difference between them and us would not be one of biology or intelligence, but of context. We are creatures of a crowded cosmos, driven by connection. They would be children of isolation, born into silence. To live in the Boötes Void would be to experience the universe not as a network, but as a monologue, a single voice echoing endlessly in the dark. And yet perhaps that solitude would bring a kind of clarity we have lost. In a world without distraction, meaning might be sharper. In a sky without neighbours, every star would matter more. Within the Boötes Void, existence itself would be an act of defiance. A lone light insisting against all probability that even nothingness can give rise to life. When scientists map the large-scale structure of the universe, they find that galaxies are not scattered randomly through space but arranged in an immense, interconnected network known as the cosmic web. It is a structure of extraordinary beauty and complexity, threads of matter, stretching for hundreds of millions of light years, weaving together to form clusters, filaments, and vast empty spaces in between. In this grand architecture, the Boötes Void appears not as an isolated anomaly, but as one of the web's great hollow chambers, a bubble carved out by the gravitational dynamics of the universe itself. To understand the void, one must first understand the web, for they are not opposites but partners in creation. Every cluster of galaxies implies a corresponding void, every concentration of matter a compensating absence. The cosmic web is balance incarnate, structure defined by emptiness, light framed by darkness. The web's origin traces back to the earliest moments after the Big Bang. In the newborn universe, matter was distributed almost evenly, with only tiny ripples, minute variations in density left over from quantum fluctuations during inflation. Over time, gravity amplified those ripples, drawing slightly denser regions together while slightly emptier ones expanded. The denser pockets became the seeds of galaxies, clusters, and superclusters, while the emptier regions grew into voids. What emerged was a cosmic network reminiscent of neurons or mycelium, a pattern that repeats across every observable scale. Even our Milky Way sits on one of these filaments, a thin strand connecting larger nodes of galactic density. The Boötes Void, however, stands apart, not because it defies the web, but because it exemplifies its structure in the extreme. It is what happens when the balance tips entirely toward emptiness. When visualized through computer simulations, the cosmic web looks almost organic, an ethereal tangle of glowing filaments separated by vast black gaps. The Boötes Void, seen within this lattice, resembles a swollen cell in a living organism, its spherical emptiness pressed against the walls of neighbouring structures. This analogy is not merely poetic, it reflects a fundamental truth about how gravity and dark energy interact. The web is dynamic. Filaments feed galaxies with gas, galaxies merge into clusters, and voids grow by draining matter from their interiors into the surrounding network. Over cosmic time, this process becomes self-reinforcing. The rich grow richer, and the empty become emptier. The Boötes Void is thus both a product and a victim of cosmic evolution, a region that has lost the competition for matter so completely that it now drifts toward perfect vacuum. Astronomers mapping the web often describe its structure in terms of walls and nodes. Superclusters like Hercules, Coma, and Corona Borealis form the massive walls surrounding the Boötes Void. These are not discrete boundaries, but regions of high galactic density, where the gravitational pull of billions of stars holds the line between fullness and absence. Inside that border, the density of galaxies drops sharply, by a factor of hundreds compared to the cosmic average. The transition is abrupt, almost like crossing from a city into a desert in a single step. Yet the geometry remains smooth. The void's walls curve inward with graceful continuity, suggesting that the surrounding filaments have pressed against it evenly for billions of years. It is this symmetry, this uncanny perfection, that makes the Boötes Void so distinct from other hollows in the web. It is not chaotic or ragged, but calm, as if the universe itself took care in crafting its boundaries. The cosmic web is more than a visual metaphor. It is a physical manifestation of gravity's long game. The filaments that define it are composed not just of galaxies, but of dark matter, an invisible scaffold that dictates how visible matter arranges itself. Dark matter is what binds the web together, shaping its filaments and stabilizing its nodes. Without it, galaxies would drift apart and the web would dissolve into random distribution. Inside the Boötes Void, however, even dark matter is sparse. Computer models predict that its interior density may be less than 1/10 of the cosmic average, meaning that not only ordinary matter, but also the invisible mass underpinning the cosmos is largely absent. The void is not merely an absence of light, it is an absence of the invisible as well. In recent decades, astronomers have begun to see the cosmic web as the universe's fundamental architecture, the skeleton on which everything else is built. When large-scale surveys like the Sloan Digital Sky Survey mapped millions of galaxies, the resulting 3D maps revealed filaments hundreds of millions of light-years long, converging into dense clusters and separating vast voids like Boötes. The discovery transformed cosmology. Suddenly, the universe looked less like a random sprawl and more like a designed lattice and interlocking pattern governed by simple, universal laws. Yet within that order, the Boötes Void remains a point of mystery. Its size and uniformity challenge even the best simulations, suggesting that either the initial fluctuations were more extreme than expected, or that new physics operates on these scales. It stands as the web's silent heart, the point where the pattern becomes paradox. Philosophically, the cosmic web blurs the line between fullness and emptiness. Its beauty lies not in the galaxies themselves, but in the way they outline the nothing between them. The Boötes Void is part of that symmetry, a necessary counterweight to creation. In the same way that silence gives shape to music, the void gives meaning to the web. Without these vast hollows, the clusters and filaments would have no contrast, no rhythm, no form. The universe, in its grand design, seems to demand balance matter and antimatter, light and darkness, density and emptiness. The cosmic web is the visible echo of that balance, and the Boötes Void is its most eloquent silence. It is the pause between cosmic notes, the quiet that allows the symphony of galaxies to be heard at all. Beneath the visible universe, the galaxies, stars, and nebulae that fill our telescopes, there exists a hidden framework that dictates everything we see: dark matter. It does not emit or absorb light, cannot be touched or seen directly, yet it makes up roughly 85% of all matter in existence. Without it, galaxies could not hold themselves together, the cosmic web would collapse, and the universe as we know it would be nothing more than a chaotic mist. In this unseen lattice lies the true architecture of reality, a colossal skeleton of invisible mass stretching across space and time, and nowhere does its absence speak louder than in the Boötes Void. For if the universe is built upon a skeleton of dark matter, then the Boötes Void is the place where that skeleton seems to thin, bend, or vanish altogether. The first hints of dark matter's influence came not from grand voids, but from the humble rotation of galaxies. Astronomers noticed that stars at the edges of spiral galaxies orbit their centres far faster than visible matter alone could explain. There had to be something unseen, some hidden mass providing extra gravity. Later, when scientists began to model the large-scale structure of the cosmos, they found that ordinary matter, composed of protons, neutrons and electrons, could not have clumped together fast enough after the Big Bang to form the galaxies we see today. only the presence of an invisible, non-interacting component dark matter could seed the process. It gathered first, forming halos that drew in gas, igniting star formation, and weaving the luminous threads of the cosmic web. Every filament of galaxies we observe is strung along these dark scaffolds. In a sense, the universe is not made of light, but merely illuminated by it. Within this framework, the Boötes Void represents an extremer region where even dark matter is scarce. Computer simulations of cosmic evolution show that dark matter flows along the web's filaments, much like water through a river system. It gathers in nodes, drains from underdense regions, and forms long interconnected bridges across the cosmos. Voids emerge where these flows diverge, leaving behind near-empty basins. Over billions of years, gravity amplifies the contrast between dense and empty, deepening the hollows and fattening the filaments. The Boötes Void, then, is a place where that gravitational river has run dry, a basin so vast that nearly all the dark matter has drained away. Its emptiness is not just visual but structural. Even the invisible backbone of the universe is missing. To find such a cavity in the cosmic skeleton is to discover an anatomical anomaly, a missing bone in the body of creation. Scientists attempt to probe this absence indirectly, by measuring how light from background galaxies bends as it passes around or through the Boötes region, phenomenon called gravitational lensing. They can infer how much mass, both visible and dark, lies along the path. These studies consistently show that the void contains far less matter than expected. The lensing effect is minimal, confirming that even dark matter density is dramatically reduced. Yet this result introduces a paradox. If the void truly lacks dark matter, what prevents it from collapsing or being refilled over cosmic time? Gravity should have pulled nearby material inward long ago. The fact that it remains so perfectly empty suggests an equilibrium maintained by the universe's expansion, a delicate balance between the pull of matter and the push of cosmic acceleration. The Boötes Void, in this sense, may not be a passive cavity, but an active region, where the forces of creation and expansion meet in perfect opposition. The absence of dark matter also alters the rhythm of time and energy inside the void. Without significant gravitational potential, space-time there is smoother, less curved. Light moves more directly, time flows marginally faster, and the cosmic expansion acts unopposed. If dark matter defines the skeleton of the universe, then the Boötes Void is a gap between bones and open space where the fabric stretches freely, unanchored by the invisible mass that shapes most of the cosmos. This freedom may explain its uncanny symmetry. With no gravitational irregularities to distort it, the void expands evenly, maintaining its near-spherical perfection over billions of years. In a strange way, its smoothness is proof not of chaos, but of order, a natural outcome of near-perfect absence. Some theorists have speculated that the Boötes Void might conceal an even deeper mystery. If dark matter is truly the cosmic skeleton, perhaps this region marks a fracture or flaw in that skeleton, a place where the physics governing dark matter itself behaves differently. Could it be that the particles of dark matter interact less efficiently here, or that the field governing them is weaker? Certain models of modified gravity and scalar field dark matter suggest such anomalies could exist, rare pockets where dark matter density dips dramatically due to quantum or field effects. If verified, the Boötes Void might not just be a geographic oddity, but evidence of new physics, a sign that the invisible scaffold of the universe is not as uniform as we assume. From a metaphorical perspective, the Boötes Void embodies the relationship between structure and emptiness that defines the cosmos. The dark matter skeleton provides shape, but the void gives meaning. It is the space between bones that allows movement, the emptiness between galaxies that allows expansion. The universe's beauty lies not in matter alone, but in the delicate interplay between what is present and what is not. Without voids, the web would be formless. Without dark matter, it would be shapeless. Together, they create the architecture of existence, a balance between visibility and invisibility, between substance and nothingness. Standing at the edge of the Boötes Void, in imagination if not in reality, one might sense this balance as something profound. On one side lies the cosmic web, glowing with the accumulated light of galaxies bound to the unseen skeleton. On the other side lies the hollow silent, invisible infinite. The transition is not abrupt but gradual, a fading from form into formlessness. There, at the boundary, the universe reveals its dual nature, a body made of dark matter and a soul made of void. The Boötes Void is where those two halves meet, where the skeleton of reality gives way to pure space. It is the pause between gravitational heartbeats, the place where the universe breathes. The question that has haunted astronomers since the discovery of the Boötes Void is simple but profound. How did it come to be? The universe, vast as it is, should not permit such an enormous cavity to exist within the short span of its history. The problem is not that voids are rare, they are in fact natural byproducts of cosmic evolution, but that this one is simply too large, too symmetrical, too empty. Over the decades, several theories have attempted to explain its origin, ranging from conventional astrophysics to ideas that border on the speculative, even the metaphysical. Each new hypothesis brings insight, yet none have resolved the riddle completely. The Boötes Void remains an open wound in cosmology, a silent challenge to the coherence of our models. The first and most traditional theory holds that the Boötes Void formed through the gradual merging of smaller voids. In this view, early in cosmic history, the universe contained numerous small underdense regions like bubbles in a frothy fluid. As space expanded, these bubbles grew and coalesced, forming larger and larger cavities. Over billions of years, the mergers produced supervoids such as Boötes. This explanation fits comfortably within the framework of standard cosmology and matches computer simulations up to a point. The problem, as simulations repeatedly demonstrate, is one of scale and smoothness. Even when smaller voids merge, their boundaries remain irregular. The resulting structures are elongated and distorted. The Boötes Void, by contrast, is almost perfectly spherical and nearly devoid of residual filaments. To produce such an object, multiple voids would have had to merge with uncanny precision, their interactions smoothing into an improbable equilibrium. Statistically, that outcome is so unlikely that some cosmologists consider it effectively impossible. Another hypothesis proposes that the Boötes Void originated from an initial density anomaly, a primordial fluctuation imprinted in the early universe before galaxies even formed. During the period of cosmic inflation, quantum fluctuations in the energy field expanded rapidly, seeding tiny variations in density. Most of these variations were small and random, but what if one was unusually extreme? A region slightly less dense than average could have expanded faster, its matter spreading thin long before stars and galaxies took shape. As the rest of the universe coalesced into filaments and clusters, this underdense pocket would have continued to expand unchecked, becoming the Boötes Void we see today. This primordial void model solves the timescale paradox elegantly. If the void began early enough, it would not need to form later. It simply always was. Yet it raises new questions. How could such an extreme fluctuation occur without leaving imprints on the cosmic microwave background? Observations show no significant temperature anomaly in the Boötes region. The void's very perfection becomes its paradox. It appears both ancient and invisible, immense yet without traceable origin. A third possibility involves the mysterious interplay between dark energy and gravity. Some researchers suggest that dark energy, the force responsible for the accelerating expansion of the universe, might not be uniform. If dark energy density was slightly higher within the Boötes region, even by a minuscule fraction, the local rate of expansion could have increased dramatically, pushing matter outward and deepening the void over billions of years. This would make Boötes a kind of natural experiment in cosmic acceleration, a place where the universe's expansion briefly outran its own average. But no observational evidence yet supports the idea of regional variation in dark energy. Its measured constancy across vast distances argues against such a mechanism. Still, the possibility lingers, especially among cosmologists who suspect that dark energy may evolve subtly over time or interact with matter fields in ways we do not yet understand. If that is true, then the Boötes Void may be our first direct glimpse of that interaction, a scar left by the universe's uneven acceleration. There are two more radical theories ideas that step outside conventional cosmology. Some physicists have speculated that the Boötes Void might represent the remnant of a cosmic collision, where our universe once brushed against another during or after the inflationary epoch. In the inflationary multiverse model, countless bubble universes expand simultaneously within a higher dimensional space. If two bubbles were to collide, the impact could leave behind a region of altered density, a scar imprinted on the cosmic fabric. The Boötes Void's near-perfect geometry and scale fit the predicted signature of such an event. From this perspective, what we call a void might actually be a boundary, a place where another universe once touched ours before drifting away. The idea is speculative, bordering on the metaphysical, but it resonates with the void's uncanny symmetry. It would mean that the Boötes Void is not merely an absence, but an interface, a fossilized contact between realities. Still others take a more philosophical approach, suggesting that the Boötes Void represents not a failure of cosmology, but an inevitable consequence of it. The universe, they argue, is governed by principles of symmetry and balance. Where there is light, there must be darkness. Where matter accumulates, space must clear. The Boötes Void may simply be the natural counterweight to the universe's grandest clusters, a necessary emptiness to preserve equilibrium on cosmic scales. In that sense, its existence is not anomalous at all, but inevitable. It is the cosmos expressing its need for contrast, just as silence defines music. This idea does not explain the physics, but it gestures toward a deeper harmony underlying the universe's design. What unites all these theories, scientific and philosophical alike, is a shared recognition that the Boötes Void stands at the limits of comprehension. It is a region where models falter, where mathematics begins to whisper instead of speak. Whether it formed from merging voids, primordial fluctuations, or cosmic collisions, its presence demands humility. The void reminds us that understanding the universe is not the same as mastering it. Some questions may remain open not because they are unsolvable, but because they are meant to reveal the boundaries of our sight. The Boötes Void may be one such question, a cosmic mirror reflecting both the universe's vastness and the limits of the human mind. Among the more audacious explanations for the Boötes Void's existence is the notion that it may not belong entirely to our universe. According to certain cosmological models, particularly those derived from inflationary theory, our universe could be just one of countless bubbles expanding within a vast multiversal foam. Each bubble represents a self-contained cosmos, governed by its own physical laws, constants, and dimensions. Occasionally these bubbles may collide. When they do, the contact can leave immense scars regions of altered density, distorted space-time, or even partial annihilation etched into the expanding fabric of both universes. To some theorists, the Boötes Void fits this description with uncanny precision. A spherical region hundreds of millions of light-years across, smoother than expected, almost as if its interior had been erased or overwritten by another universe's touch. The idea stems from the inflationary multiverse hypothesis, a consequence of the same theory that explains the Big Bang's rapid expansion. During the first fraction of a second after creation, space itself inflated exponentially, stretching quantum fluctuations to cosmic scales. In many versions of this model, inflation does not stop everywhere at once. Instead, it continues eternally in some regions, spawning endless pocket universes that bubble into existence within a larger inflating background. Each of these bubbles expands at tremendous speed, sometimes colliding with others before drifting apart into the void of higher dimensional space. Such collisions, if they occur, would leave distinct signatures, spherical voids, temperature anomalies in the cosmic microwave background, or gravitational distortions invisible to normal light. The Boötes Void, with its nearly perfect geometry and immense emptiness, matches what some simulations predict as the residue of a multiversal impact. If such an event happened, what would it mean for us? Imagine, billions of years ago, two universes brushing against each other, ours, newly born, and another, equally young. The collision would have unleashed unimaginable energies, but because the expanding space itself was involved, the interaction may not have produced heat or radiation in the conventional sense. Instead, it could have smoothed out a vast region, diluting matter and dark matter alike, leaving behind a perfectly symmetrical scar, a cavity in space-time. Over eons, as galaxies formed and clustered elsewhere, this region would remain almost untouched, expanding with the universe but never refilling. To future astronomers, it would appear as a void, an anomaly in an otherwise consistent cosmos, a silent mark left by something that existed before time as we know it. The multiverse collision hypothesis, though speculative, offers intriguing explanatory power. It accounts for the Boötes Void's scale, symmetry, and smoothness features that resist conventional gravitational models. It also aligns with the physics of inflation, which naturally produces such collisions in its eternally expanding landscape. However, it introduces new complications. For one, if another universe once touched ours, its physical laws might differ slightly from our own. The interface region could contain subtle deviations in fundamental constants, variations in particle masses, the strength of gravity, or the rate of cosmic expansion. Yet no such anomalies have been detected in or around the Boötes region. The cosmic microwave background shows no clear signature of a multiversal scar there. Its temperature map remains smooth, with no abrupt discontinuities or gravitational imprints strong enough to indicate an inter-universal event. The data, at least for now, neither confirm nor deny the hypothesis. The Boötes Void keeps its silence. Still, the collision model captures the imagination because it transforms the void from an absence into an artifact. Instead of a region that never formed galaxies, it becomes the relic of something that happened before galaxies existed at all. A cosmic archaeology site marking a moment when two realities briefly touched. Some physicists liken it to a bruise on the skin of the universe, the after effect of impact, visible long after the pain has faded. Others compare it to a window, a transparent region where the fabric between universes thinned, allowing one to glimpse the underlying void beyond. If so, then the Boötes Void might not be an emptiness at all, but a threshold, a place where the boundaries of existence briefly blurred. It would mean that our universe, for all its apparent self-containment, is not alone. We may live inside a single cell of a larger cosmic organism, one bubble among innumerable others floating in an infinite sea. Philosophically, this concept reshapes the meaning of emptiness itself. If the Boötes Void is a scar of contact between universes, then what appears to us as nothing is, in truth, the residue of something greater. It reframes the void not as failure or absence, but as testimony proof that creation extends beyond our cosmos, that the universe we inhabit may have siblings, ancestors, or descendants we can never reach. It also challenges the idea of isolation. In a multiverse, no universe is truly alone. Each exists as part of an ever-growing family of realities. From that perspective, the Boötes Void might be the first tangible evidence of cosmic kinship, a silent reminder that our universe once brushed against another and carries the memory still. Critics of the multiverse model point out that it borders on metaphysics. Because other universes lie beyond observational reach, their existence may remain forever untestable. Without direct evidence, without measurable imprints in the cosmic microwave background or gravitational wave data, the idea risks remaining elegant but unprovable. Yet science has long relied on inference, on the unseen deduced from the seen. Once, the existence of atoms, black holes, and dark matter were all considered speculative too. The absence of light within the Boötes Void could someday prove to be the first hint of something equally revolutionary, a structure not born of our own cosmos, but of one that passed close enough to leave its shadow behind. In the end, whether or not the Boötes Void is the scar of another universe, the theory carries a poetic truth. It reminds us that even emptiness may have a history. The void becomes not an error of creation, but a footprint of it, a relic of forces that shaped not just our space but all spaces. To gaze into that immense darkness is to confront the possibility that our universe is only one note in a far grander symphony, a vibration in an infinite chorus of worlds. And in that thought lies both wonder and humility, the recognition that what we call the universe may not be the whole, but merely the part of everything that happens to contain us. Silence is not merely the absence of sound, it is a state of being, a kind of presence that can weigh as heavily as noise. Nowhere in the cosmos is that more evident than within the Boötes Void. If one could somehow exist there floating between its few lonely galaxies, suspended in the abyss, the silence would be absolute. No wind, no echo, no pulse of radiation loud enough to touch the senses. Even the faint hiss of cosmic background noise would seem swallowed by distance, diffused across hundreds of millions of light years. It would be a silence so vast it would seem alive, pressing inward like a thought that cannot be spoken. The Boötes Void is not merely a lack of matter. It is the embodiment of stillness, a cathedral built of absence where every whisper of the universe falls mute. In such an environment, Even light, the most constant traveller of space, moves differently. Photons pass through without resistance, but without matter to scatter them, there is no glow, no shimmer, no reflection. A single beam from a distant galaxy would cross that void like a ghost through darkness, unseen except by the faintest instruments. The few galaxies within the void radiate into an emptiness that never replies. Their light travels outward endlessly, likely never to be intercepted by another eye, another world, another being. In the cosmic symphony, the Boötes Void is a pause of infinite duration, a rest so long it seems eternal. It is silence not as emptiness but as endurance, the quiet that remains after all motion has exhausted itself. Scientists often speak of the void in mathematical terms: density contrasts, gravitational potential, expansion rates. But beyond the equations lies a more human awe. The Boötes Void is a confrontation with the limits of comprehension. When telescopes stare into it, they return almost nothing, no structures, no clusters, no foreground noise to interpret. The data is an absence, a blank on the map that feels more like a mission than discovery. It is as if the universe itself hesitates there, as though creation skipped a beat. That silence, paradoxically, speaks volumes. It reminds us that not all truths are expressed through presence. Some are revealed through what refuses to appear. Philosophically, the silence of the Boötes Void invites reflection on our relationship with nothingness. Humanity has always feared silence, sought to fill it with words, music, or light. Yet silence, on cosmic scales, is the natural state of things. The noise of stars and galaxies, the radiation, collisions, and bursts we can detect is the exception. The background hum of the universe is cold and low, a frequency barely above zero. In that sense, the Boötes Void is not an anomaly, but a mirror held up to reality's fundamental condition. The universe began in a moment of unimaginable energy, but it has been cooling and quieting ever since. The Boötes Void is a glimpse of the future written in the present, a foreshadowing of the long silence to come when all stars have burned out, and even light itself has nowhere left to go. From a psychological perspective, this silence touches something primal. When early astronomers first grasped the scale of the void, their reactions bordered on existential dread. Here was not just a gap in space, but a chasm in meaning. For centuries, humanity had comforted itself with the belief that the universe, though vast, was filled with stars, with structure, with purpose. The Boötes Void stripped that illusion bare. It suggested that the cosmos is not an endless expanse of brilliance, but an ocean of darkness, sparsely illuminated by fragile islands of light. The silence it represents is not merely physical, but metaphysical, the silence of insignificance, of realization. To look into the void is to confront the possibility that creation's truest voice is quiet, and that our existence is a brief whisper within that stillness. For poets and philosophers, the void's silence has become an allegory. It embodies both death and transcendence, fear and freedom. In its emptiness lies both annihilation and possibility. Just as a blank page invites creation, the Boötes Void suggests that even the universe leaves space for new beginnings. The silence there is not final. It is potential waiting to be realized. Matter once filled even the emptiest corners of space before gravity drew it into stars. Perhaps, given enough time, the void will stir again. Or perhaps it will remain forever untouched, a sanctuary of stillness preserved in a universe increasingly consumed by expansion and entropy. Either way, its silence is not meaningless. It is the silence of balance, the sound of equilibrium maintained between being and nothing. Scientifically, silence has its own kind of music. Within the void, the absence of matter reduces the medium through which gravitational waves, magnetic turbulence, or plasma oscillations can propagate. Yet quantum mechanics teaches that even vacuum is never truly still. Beneath that perfect quiet hums a restless sea of virtual particles flickering in and out of existence, a subatomic murmur too faint for even the universe to hear. The Boötes Void, for all its vast emptiness, vibrates with this silent resonance, a whisper beneath silence itself. It is a reminder that the stillness of the cosmos is not dead, but alive in its own hidden way. In the end, the silence of the Boötes Void is not something to fear but to understand. It represents the space between moments, the pause between heartbeats in the rhythm of creation. Every galaxy, every atom, owes its existence to that silence, the vacuum that allowed energy to condense into matter, stars to ignite, and life to think. Without the quiet of the void, the universe would have no room to expand, no contrast against which brilliance could shine. The Boötes Void is therefore not the enemy of being, but its condition. It is the breath the cosmos takes between words. When we listen to it, truly listen, we do not hear nothing. We hear the sound of infinity resting. Every structure in the universe, from the smallest atom to the largest galaxy cluster, carries a faint memory of its birth. In the same way, the Boötes Void may be an echo and imprint left by the earliest moments of creation, stretched and magnified by cosmic time. To understand its silence and symmetry, one must return to the beginning, when the universe itself was less than a second old. In that primordial instant, space and time erupted from a singularity, expanding faster than light in an event we call inflation. During that incomprehensibly brief period, quantum fluctuations, microscopic ripples of energy, were frozen into the fabric of space. Over billions of years, these ripples grew into galaxies, clusters, and the great voids that divide them. Every corner of the cosmos today is a magnified whisper of that first quantum breath. The Boötes Void, then, may not be a coincidence at all, but the amplified echo of a particularly deep trough in the primordial symphony of creation. The cosmic microwave background, the faint radiation that fills all of space, is our record of that early song. Its delicate variations in temperature, measured in millionths of a degree, correspond to the density fluctuations that later became the architecture of the universe. The patterns etched in that ancient light reveal the universe's original composition, a map of where matter would one day gather and where it would flee. When cosmologists examine those maps, they find regions that correspond well to the observed distribution of galaxies and voids. Yet even among those vast patterns, the Boötes Void stands out as an overachievement, a space too large, too uniform, too empty compared to the early fluctuations we can detect. If it is an echo of creation, it seems to have amplified itself beyond the limits of the original tune. Something in its evolution intensified the silence, stretching a normal ripple into a chasm. Some theorists propose that the void's exaggerated form may result from nonlinear amplification, the way small initial differences can grow disproportionately large under the influence of gravity and cosmic expansion. In the early universe, matter flowed away from underdense regions toward denser ones, deepening the contrast between light and dark. If a region began with even a slightly greater deficiency of matter, its expansion rate would accelerate, making it emptier still. Over time, this runaway process could produce supervoids like Boötes, but even these simulations struggle to replicate its perfection. The Boötes Void is not jagged or filamented like smaller voids. It is smooth and almost spherical, as though the laws of chaos took a momentary pause there. For that reason, some scientists suspect that the void might preserve a more pristine imprint of the inflationary epoch than any other region, untouched, uncorrupted, and perhaps still resonating with the quantum structure of the universe's birth. The idea that the void is an echo of creation has a poetic appeal, but also a scientific one. The cosmic microwave background gives us a snapshot of the universe when it was only 380,000 years old. Everything beyond that lies hidden behind a wall of radiation. But if the Boötes Void indeed evolved directly from an ancient fluctuation, then studying its geometry, its internal dynamics, and the rare galaxies within it could reveal information about conditions before that wall. The distribution of matter in and around the void might encode the shape and spectrum of primordial waves, the same oscillations that shaped the first atoms and dictated how structure unfolded. In essence, the Boötes Void could be a fossil of inflation, a preserved cavity that still holds the fingerprint of creation's first vibration. Astronomers have begun to approach this possibility with refined tools. By mapping the three-dimensional distribution of galaxies across billions of light-years, they reconstruct the cosmic density field and trace the outlines of primordial fluctuations. In this grand reconstruction, voids act as negative space, the inverse images of clusters. Their size and distribution reveal how gravity and dark energy have sculpted the universe over time. When the Boötes Void is placed within this map, it appears not as an isolated bubble, but as a harmonic anomaly, a region whose wavelength and amplitude do not fit the surrounding pattern. It is as if the universe hit a single deeper note in that place, a sound so low it can only be heard through its absence. Beyond the scientific implications, the notion of cosmic echoes touches something deeply human. It reminds us that everything we see, the stars, the galaxies, even ourselves, is reverberation. The hydrogen in our blood once oscillated as radiation in the infant universe. The atoms that compose our bones carry the rhythm of that first expansion. The Boötes Void, in its majestic emptiness, is part of that same music. It represents the pause between cosmic beats, the silence that allows the next chord to resonate. If the early universe was a song of creation, the void is its lingering echo, one that has travelled through time for nearly 14 billion years, growing fainter but never dying out. In this sense, the Boötes Void can be seen not as a mistake or an accident, but as a remnant of cosmic harmony. It is the negative image of the universe's first sound, a hollow where the energy of creation passed and left stillness in its wake. Perhaps one day we will develop instruments sensitive enough to hear that silence, to detect the gravitational or quantum ripples still resonating within its depths. If that day comes, we will not merely observe the Boötes Void, we will listen to it. We will hear, in the quiet between galaxies, the echo of the beginning, the breath of the cosmos captured in the geometry of nothingness. The Boötes Void is often described as a window into the universe's past, but it also offers a glimpse of its future. To look into that immense hollow is to see a reflection of what the cosmos is becoming. The forces that created it, expansion, entropy, and the relentless thinning of matter, are the same forces that will eventually define everything. In that sense, the Boötes Void is not merely a relic of creation, but a prophecy of dissolution. It shows us how the universe ends, not with collapse or fire, but with silence, distance, and the slow fading of light. The void is the seed of eternity, a region where time itself may already be unravelling faster than elsewhere, slipping toward the inevitable stillness that awaits all things. Cosmologists describe this destiny in terms of dark energy, the mysterious component that drives the accelerating expansion of space. As galaxies move farther apart, the distances between them increase at an ever-growing rate. One day, billions or trillions of years from now, each galaxy will drift beyond the horizon of every other, vanishing from view as their light can no longer cross the expanding gulf. The Boötes Void, with its vast emptiness and scattered survivors, is a small-scale preview of that ultimate state. What it represents locally will one day become universal. Every region of the cosmos will become its own private Boötes Void, isolated and dark, its inhabitants, if any, remain forever cut off from the rest of creation. The universe will fragment into islands of light adrift in a limitless ocean of nothingness. This fate, often called the heat death or big freeze, is not an explosion but a dissipation. Over unimaginable timescales, stars will exhaust their fuel, galaxies will grow cold, and black holes will evaporate into radiation. Eventually, all structure will dissolve into a thin mist of particles spread too sparsely to interact. Even time will lose meaning when change itself ceases. The Boötes Void, therefore, is not merely a place in space, but a premonition of that era a laboratory where the universe's final conditions already exist. Inside it, the processes that will one day dominate everywhere are already at work. The isolation of galaxies, the absence of gravitational interaction, the supremacy of expansion over cohesion. To peer into the Boötes Void is to look billions of years into the future, to witness a local rehearsal of the cosmic end. In that future, time itself may fracture. Einstein's theory of relativity tells us that time flows differently depending on gravity and motion. In dense regions where mass bends space-time strongly, time moves slightly slower. In empty regions where space stretches freely, it moves faster. In the Boötes Void, one of the emptiest expanses in existence, time may already be ticking ahead of the rest of the universe by imperceptible amounts. It is a region where the cosmic clock runs loose, unanchored by the weight of matter. As the cosmos ages and empties, that condition will spread. The pace of time will accelerate as density declines, stretching moments thinner and thinner until they lose all distinction. The end of time will not come suddenly, but will fade in slowly as the rhythm of change slows into stillness. The Boötes Void may thus be the first whisper of temporal death, a region where time is already dissolving into eternity. Yet the notion of an end in a universe that continually expands invites paradox. If time loses meaning, does the universe truly end? Or does it simply enter a state beyond change, an infinite persistence of silence? In some interpretations of quantum cosmology, the ultimate fate of the universe resembles not annihilation but stasis. The vacuum becomes the dominant state, cold, homogeneous, featureless, and the quantum fluctuations that once seeded galaxies fade below detectability. The universe does not die, it rests. It becomes a cosmic Boötes Void, writ large and endless tranquil expanse of low energy, where every particle has drifted too far to meet another. In that sense, the Boötes Void is a portrait of the universe's last breath held forever, a fragment of tomorrow existing today. The human imagination struggles with such scales. To envision 1 trillion years, let alone the eternity beyond, is to reach the edge of thought itself. Yet there is a strange comfort in this idea. The Boötes Void, in its cold perfection, reveals that even the universe's death will not be violent. It will fade gently, not explode. There will be no apocalypse, no sudden void swallowing existence, but a gradual quieting, a return to equilibrium. Energy will disperse evenly, matter will thin to invisibility, and the last photons will stretch into wavelengths longer than the universe itself. Darkness will not conquer light. It will simply outlast it. The void will win not through destruction, but through patience. Still, some physicists resist the finality of this vision. They speculate that quantum effects could eventually reignite the cosmos, that within the emptiness, random fluctuations might trigger new bursts of creation, new universes budding like bubbles from the cooled residue of the old. In this cosmic rebirth scenario, the Boötes Void might not signify the end of time, but the womb of another beginning. Perhaps every great emptiness is pregnant with potential, every void a prelude to renewal. If so, then time itself may be cyclical, eternally oscillating between fullness and emptiness, light and silence. The Boötes Void would then be not a tomb but a seed proof that even in the deepest darkness, the universe preserves the memory of creation and the possibility of another dawn. Whether it foretells final stillness or eternal recurrence, the Boötes Void remains a kind of mirror for the destiny of all things. Its quiet expanse reminds us that the universe, despite its brilliance, is defined not by its stars but by its spaces between them. The end of time will not erase meaning, it will reveal it, the truth that existence and emptiness are partners in the same dance. The Boötes Void is the rehearsal for that final act, the first glimpse of a universe learning how to rest. The Boötes Void is not only a cosmic phenomenon, it is a mirror, one that reflects the deepest aspects of human thought and feeling. To confront such immensity, such quiet absence, is to face ourselves. We are creatures of contrast, beings of light who define meaning by the shadows that surround it. In that sense, the void outside us echoes the void within. The vast emptiness between galaxies mirrors the spaces between our thoughts, our doubts, our moments of silence. The Boötes Void does not merely invite astronomical curiosity, it demands existential reflection. When we gaze into that darkness, what we find is not only the absence of stars but the reflection of our own smallness, and paradoxically our own magnitude in being able to perceive it. For millennia, humanity has sought to fill the universe with purpose, gods, patterns, stories that impose order upon the infinite. Yet the Boötes Void resists interpretation. It is too large to be reduced to symbol, too empty to be conquered by metaphor. It humbles even the imagination. In its silence, we are reminded that the cosmos owes us no meaning, that its beauty does not depend on comprehension, and yet, in acknowledging this, we create meaning ourselves. The act of looking into the void transforms it. To observe the emptiness is to bridge it. To understand the silence is to give it a voice. In this way, the Boötes Void becomes the ultimate canvas for human consciousness, a place where thought meets nothingness and, in doing so, becomes something. Science approaches the void with instruments and equations, but emotion approaches it through awe. Awe is not ignorance, it is recognition of the scale of what we cannot yet hold in our minds. Standing before the idea of the Boötes Void, we are not diminished but expanded. The mind stretches to accommodate an image of space so immense that comprehension itself falters. It is in that faltering that wonder lives. The void teaches humility, but not despair, silence, but not meaninglessness. It shows that emptiness can be fertile, that the absence of form can give rise to imagination. When astronomers chart the galaxies scattered within that hollow, they are not just measuring cosmic distances, they are performing an act of communion with the unknown. Philosophers have long wrestled with the nature of nothingness. For the ancient Greeks, the void was terrifying, an impossible vacuum that contradicted existence. For Eastern thinkers, it was sacred and openness that made being possible. In the Boötes Void, these two traditions meet. It is both terror and transcendence, both the cold face of oblivion and the serene space of potential. The void exists not to erase meaning, but to make it necessary. Without it, the universe would be dense, uniform, suffocating, no place for difference, no space for life or motion. Emptiness is what allows creation to unfold. The Boötes Void is thus not the failure of the universe, but its condition. In its silence lies the possibility of everything else. Viewed from this perspective, humanity's awareness of the void becomes a cosmic event in itself. Life, consciousness, and reflection are the universe's way of noticing its own architecture. Through us, the universe observes its emptiness and asks what it means. The Boötes Void, then, is not separate from us. It is part of the same process of self-awareness that gave rise to thought. When a human being contemplates that vast hollow, the act is not trivial. It is the cosmos momentarily turning inward. We are atoms that have learned to look back at the abyss from which they came. The silence of the Boötes Void and the silence of our inner contemplation are two expressions of the same phenomenon. The universe pausing to listen to itself. Artists, poets, and dreamers have always been drawn to emptiness. In the blankness of a canvas, the stillness of a night sky, or the pause between musical notes, they recognize the same truth. Creation begins where noise ends. The Boötes Void can be seen as the greatest blank canvas of all, a masterpiece of restraint, painted not with colour but with absence. To imagine it is to confront the paradox of creation itself, that something somehow emerged from nothing. Every human story, every work of art, every discovery of science is, in a sense, a rebellion against that nothing, a refusal to let silence have the final word. Yet even as we fill the void with meaning, we depend on it. Without silence, there can be no sound. Without the Boötes Void, the galaxies that encircle it would lose their shape. Without the mystery, knowledge would lose its purpose. Perhaps then the ultimate lesson of the Boötes Void is reconciliation. It invites us to accept that fullness and emptiness, life and absence, are not opposites, but partners. The void is not an enemy to be feared or a puzzle to be conquered. It is a teacher, reminding us that beauty can arise from balance, that the universe's grandeur is inseparable from its quiet. To understand the Boötes Void is to recognize that meaning does not depend on density. Even nothingness can be perfect. Even silence can be complete. And so, as we stand on our small planet, one of billions orbiting stars scattered across filaments that span the cosmic web, we can look into the Boötes Void and feel both lost and found. Lost, because its scale erases every human boundary. Found, because in perceiving it, we participate in something greater than comprehension. The void gazes back, not with hostility, but with indifference so vast it becomes peace. Its darkness does not consume us, it completes us. The Boötes Void is the universe's deepest mirror, and when we peer into it long enough, what we finally see is not nothing but ourselves, reflected in the silence of creation.